In this lab, our objective was to find the coefficient of kinetic friction between our black lab tables and a given card we were given with a known mass. The materials we were allowed to use were a meter stick, 4 defined masses of masses 100 grams, 200 grams, 500 grams, and 1 kilogram, a string we assumed to be massless, and a pulley. So our setup consisted of a card on the lab table and a known mass hanging off of the pulley at various distances from the pulley. We picked the surface of the floor to be the place where the gravitational potential energy would be defined to be 0. So how did we go about solving our task? Our plan was centered around calculating the change in position of the block on the table. By defining our system to be both the card on the table and the hanging mass, we were able to ignore the internal tensional force. We divided our experiment into 2 phases, the first phase being before the hanging block stopped moving, and the second phase consisting of the overshoot of the block on the table after the hanging block stopped moving. In the first phase, we utilized the concept that the work done by friction is equal to the change in mechanical energies of the initial and final states to set up an equation relating mu sub k and velocity. In the second phase, the only force acting on the block was friction, so we were able to set up another equation relating mu and velocity. Thereby, we were able to set our 2 equations equal and solve for the velocity and mu sub k. Like in any good experiment, we defined several variables. The first variables we defined were related to mass. M sub 1 was defined to be the mass of the hanging block, and M sub 2 was defined to be the mass of the card on the table. We also defined several distances. H was defined to be the initial height of the hanging mass M sub 1 above the surface of the floor. The distance the card traveled before overshoot was defined to be D sub 1. Since the hanging mass stops moving right before the card starts to overshoot, D sub 1 is equal to H. D sub 2 was defined to be the distance the card traveled during overshoot. Together, D sub 1 and D sub 2 comprise the total distance the card on the table traveled, which we defined to be D sub t. The calculations for phase 1 of our experiment consist of the time from when the system just starts moving to when the hanging mass stops moving, or when the card just begins overshoot. Initially, there is no kinetic energy, since the system is at rest. There is, however, gravitational potential energy both from the hanging mass and the card. However, we will choose to ignore the gravitational potential energy of the card, since the card does not change in height in the course of the experiment. Therefore, the initial mechanical energy of the system is m sub 1 times g times h. Right before the end of phase 1, the system is traveling with velocity v. Here, there is no gravitational potential energy except for the card above the table, which we choose to ignore as stated before, only kinetic energy. Hence, the mechanical energy at this phase is 1/2 times the mass of the system, which is m sub 1 plus m sub 2 times v squared. Since friction is a non-conservative force, it does work on the system during the course of phase 1. Therefore, the change in mechanical energy in phase 1 is equal to the work done by friction. With simple yet tedious algebra, we find that mu sub k is equal to the quantity m sub 1 gh minus 1/2 times m sub 1 plus m sub 2 v squared all over m sub 2 times g times h. We do a similar analysis in phase 2 of the experiment, when the card is just beginning the overshoot phase. In the beginning of this phase, there is no kinetic energy from the hanging mass, since it stopped moving. Additionally, there is no gravitational potential energy from the hanging mass. Thus, the only mechanical energy is from the card on the table, which is 1/2 times m sub 2 times v squared. After the overshoot phase, when the card stops moving, there is no mechanical energy in the system. Since friction is a non-conservative force, it does work on the system during the course of phase 2. Therefore, the the change in mechanical energy in phase 2 is equal to the work done by friction. Therefore, we can set up an equation relating the previous facts. The work done by friction, which is mu sub k times F sub n times d sub 2, is equal to 1/2 times m sub 2 times v squared. F sub n is just the normal force from the table, and F sub n is equal to m sub 2 times g. Solving for v squared, we find that v squared is equal to 2 times mu sub k times g times d sub 2. So in our phase 1 calculations, we calculated that mu sub k is equal to the quantity m sub 1 times g times h minus 1/2 times m sub 1 plus m sub 2 times v squared divided by the quantity m sub 2 times g times h. In part 2, we calculated that v squared is equal to 2 times mu sub k times g times d sub 2. By plugging in our expression for v from phase 2 calculations into our phase 1 expression, we find that after some tedious algebra that mu sub k is equal to the quantity m sub 1 times h all divided by m sub 2 h plus m sub 1 plus m sub 2 times d sub 2. So we performed 6 different trials with varying values of m sub 1 and m sub 2. The results of our experiment should be pretty self-explanatory. The masses are measured in grams and the distances in centimeters. Okay, so using the values of the variables we developed in the previous slide, we are able to calculate the value of mu sub k for our various trials. I'll just reiterate the expression we developed for mu sub k in case if you guys forgot. So mu sub k is equal to m sub 1 times h divided by the quantity m sub 2 times h plus m sub 1 plus m sub 2 times d sub 2. So in trial 1, our mu sub k value was found to be 0.6764. In trial 2, it was 0.1910. Trial 3, 1.868. Trial 4, 0.5375. Trial 5, 0.1253, and Trial 6, 0.4136. However, we chose to ignore the results from Trials 2, 3, and 5 since they were outliers. So instead we just used the trials from 1, 4, and 6 to find our average mu sub k. Our average mu sub k was found to be 0.5363. So reflecting on our experiment, our answer does make sense, since the coefficient we calculated wasn't too high and it wasn't insanely low. We did expect the coefficient to be lower, however, because as we all know, the lab table is very smooth and objects tend to move around it very easily. Of course, this discrepancy can be attributed to a myriad of errors. For example, there may have been mismeasurement, lab inaccuracies, also known as human errors in our experiment. Of course, these are not controllable and probably affected our result in undesired ways. In addition, we assumed the mass of the string and the pulley to be negligible. Of course, we know from real life that this is not true, and it's never the case. However, to make our calculations even possible, we had to make this assumption. Therefore, our final result is probably a little bit off. Additionally, we did not consider the static friction right before the system started moving and the friction in the string throughout the experiment, which probably also contributed to any offness in our final result. Thank you for watching our presentation. We hope you enjoyed our discussion and we hope you learned a lot.